So, how do you tell how hot an object is by looking at the light that it's giving off? Well, we go back to what Planck was studying, looking at the colors that come out of something that's very hot, like a hot solid, or something that emits at all wavelengths, like a star. When you have something that is relatively cool, at least for a star, something like 3000 Kelvin, what you find is it gives off relatively low amounts of light down here at the radio wavelengths, more and more up through the microwave, and a great deal around the infrared. Then it gives off less and less through the visible spectrum, less in the ultraviolet, and down through the rest of the electromagnetic spectrum. This is what's called a Planck curve or a blackbody curve. The reason it's called a blackbody curve is because, if you remember, things give off the same colors that they absorb. They emit the same colors they absorb. And so if you had a perfect hypothetical black body, it would be able to absorb all colors and therefore emit all colors. This is for something that's emitting all colors at a temperature of 3000 Kelvin. Now what you're going to notice is the peak of this curve is here in the infrared, which means you'd certainly be able to feel that heat coming off of it. And if you were to look at it, notice it's giving off more red light than it is blue light. So this is an object that would look red to you. Now, what if the temperature went up? We have an object at 6000 Kelvin, and you'll notice that not only did the peak go up, so it's emitting more energy, but it's also shifted to shorter wavelengths, higher energy wavelengths, and now your peak is in the middle of the visible light. And so this object might look yellowish or even bluish. Our sun is at 5800 Kelvin. It looks rather yellow to us. Now, if you were to up the temperature again, what will happen? You can see that the peak indeed went up again and shifted over. And so for an object at 10,000 Kelvin, you'll note that it's a vigorous producer of ultraviolet radiation, and it would look blue to you. Notice that it's giving off more visible blue light than it is red, so this hotter object looks bluer. Remember that bluer is hotter, redder is cooler. This is opposite of your bathroom taps. Waves can also be used to tell how an object is moving. Here we have a stationary wave. That is, we have a source that's giving off a wave in all directions. You can imagine this is something like a star giving off, for example, yellow light in all directions. But what if the star was moving? If the star is moving through space, and imagine that you are watching it from one side or the other. If you are watching it from this side, the star appears to be moving away from you. And what happens is those wavelengths appear to be getting longer and longer, and therefore the frequencies are lower and lower. If you're on the other side and the star appears to be moving towards you, the wavelengths appear to be shorter, the frequencies higher. This means if the wavelengths are changing, the color is changing. If it's moving towards you, well, then it's getting shorter wavelengths and the star will look bluer. If it's moving away from you, the wavelengths are getting longer and the star looks redder. As a star moves towards you, it would be blue shifted. As a star moves away from you, it would be red shifted. The faster it's moving, the bigger the shift in wavelength, the bigger the shift in color. Now, this doesn't just work for light, it works for any kind of wave. You might have noticed a difference in sound, for example, with a clanging bell or with a car that goes by. If a car is coming towards you, as those wavelengths get shorter, the frequency goes up. That means your pitch is going up. As it goes away from you, the pitch goes down again. So as it comes towards you, the pitch goes up, and as it goes away, the pitch goes down. And every kid knows what that sounds like.